Good morning. Hope everybody's doing all right. Hope you had a nice weekend. Let's see, how's everybody doing? So it's warming up outside. I was happy to get outside a little bit over the weekend. Get away from a screen for a little bit. May the 4th. Excellent. A happy May the 4th to you as well. uh, May the 4th be with you. Um, let's see. So we're going to talk about momentum today. But before we jump in to that new topic, I sent out a pretty lengthy email yesterday to try and give you some clarity as we get into the last lap or two of the quarter. So my intention with that was just to give you a sense of everything else that we kind of needed to accomplish before we finish. And one of my main concerns for wrapping up is just that finals week, I'm worried a little bit that finals week may be kind of a mess. So I'm trying to anticipate that and come up with a good plan so that, um, kind of, yeah, just that you're not put in any bad positions where you're worrying about different things being due like at the same time, et cetera, et cetera. So in order to do that, I wanted to get some information from you about, uh, if you've heard things from your other faculty in terms of what they're going to do for their finals. So there's a survey on Blackboard, yet another survey. Don't worry, it'll only take you a couple minutes that I can use that to inform how we're going to do the final. I'm leaning towards basically doing something similar to what we've done with quizzes, but of course uh, it needs to be more comprehensive because it should reflect somewhat everything that we've studied. And so I'm currently working on how to do that in a logical way. Um, so please look at that survey sometime this week. Like I said, it'll only take a couple minutes, and then I'll use your input and use the kinds of questions that I've been thinking about would be appropriate for that, and finalize what's going to be on the final. Um, so let's see. Does anybody have any questions or concerns? We can spend a couple minutes on that. I'll try and be a little more rein it in a little bit, but in the interest of time and staying within our 50 minutes. But any questions, concerns, thoughts before we get rolling? Thoughts about those sort of administrative issues that I mentioned? Um, let's see. So I will follow up with people regarding labs. There's a number of missing lab exercises, but that's a thing that I'm behind on as well. It's taking me a lot longer than I would like to grade labs, just doing them all on the computer. So you will expect some more information on that front from me soon, as soon as I can get through more grading. Um, Otherwise, homework. If you have outstanding homework, there will be two more assignments. There's the one that's out now, and then there's one final one. But ones from before, if you have a missing homework assignment or something, you can still get those done and turned in for almost all of the credit. So I would encourage that as well. What other issues, outstanding issues? Yeah, like I said, if you have any concerns, if you don't have anything that you want to voice now, we can talk on Teams or via email or whatever your preferred um, way of communicating. So, no questions? Good to go? Give me your favorite weird emoji and we'll start talking about momentum. Let's do this. All right. Some good Monday enthusiasm. Um, so how many of you have heard of momentum and or momentum conservation before? Is this a topic that you've encountered? Yeah. Okay, excellent. So it sounds like this is not a foreign topic, which is good. I think of it as being a little more abstract, a little more a little less clear than energy conservation. Energy conservation to me, and I suspect to you too, comes across as quite intuitive. You have some energy. You can't destroy that energy. You can change it into different things. You can use it to do work, but it's not like the amount of energy is going to change. Um, and the context for what we're doing now is we've just talked about energy conservation. I can draw letters here. Energy conservation in the last chapter. And I had sort of harped on how this was elastic and inelastic collisions. Yes, if that terminology is at all familiar, then you've dealt with this material a little bit before, and that's good. But if it's new too, that's okay. We'll get you up to speed. So, um, to put this in context, we've just come from discussing energy conservation in the last chapter, and uh, this was I framed this to you as being easier in part because it's a scalar quantity, energy. Well, unfortunately, we're back to vectors. So that's part of why I think it makes sense to talk about momentum conservation after energy conservation. It's kind of the same idea. It's a fundamental conservation law. Something is being uh, conserved. It's remaining the same. But now we're talking about a vector quantity, momentum, rather than energy, a scalar quantity. And so what exactly is momentum? Well, there are different kinds, but the kind that we're first going to work with is the linear variety. And we usually use the letter P to represent it. And momentum is mass times velocity uh, in its sort of simplest presentation. And the units for this, so the units of this will be a mass times a velocity. So in other words, it's a kilogram meter per second. This unit has no special name or anything, so the units for momentum, in other words, are just kilograms meters per second. Um, and I would, you know, I would mention, Cedric mentions elastic and inelastic collisions. So in some sense, momentum conservation is perhaps a more fundamental situation, a more fundamental conservation law than energy conservation. So um, to try and tie a couple things together, we talked about energy conservation, and there were circumstances where energy was sort of lost, like it went into non-conservative work or work done by non-conservative forces. Um, so in other words, there are situations where energy is going to go into forms that you can't quantify very easily. Momentum, on the other hand, is always conserved. So, and that's what these terms that we will talk more in more detail about these in Wednesday, Thursday. But inelastic and elastic collision, or elastic and inelastic collisions, are collisions where you do or do not conserve energy, in addition to momentum, where momentum is always conserved. So, yeah, it's kind of an interesting thing, but I think momentum comes across as being perhaps a little more abstract, but at the same time, it's almost more fundamental in that you always conserve momentum. And another thing that I wanted to mention with regards to what is momentum, etc., is this is an excellent example um, of how calculus is really the natural language of physics. So what I mean is, so it turns out we introduced Newton's second law as sum of the forces equals ma, but we can also write it as dp dt. Now, and when Newton originally formulated his laws, granted the language he used was different, but the conceptual framework that he used, the way he was thinking about it was as a change in momentum, not as F equals ma per se. So, and the thing that's cool about this, so a couple things are cool about this, but so we just talked about how momentum is mass times velocity. So normally, mass is going to be constant. You take a derivative of this constant times velocity, you get m times dv dt. dv dt, that is acceleration. So this is the same thing as saying mass times acceleration. So this is Newton's second law. Now, we didn't write it this way initially because this requires us to use a derivative, right? We'd have to present it with a derivative from the get-go, and we wanted to kind of ease into this idea. So we first presented this in chapter 2, or not chapter 2, chapter 4, as F equals ma. But this way of presenting it, dp dt, the time derivative of momentum, is more powerful for the following reason. Well, here's one reason. Notice if the mass is not constant, then you have a product, and you would have to take a derivative of that product, and you know your rules for products. You take the derivative of the first one times the second, so you'd have dm dt, plus you'd have our normal term m dv dt. Now, what this means is that there's also going to be a change in momentum that you could attribute to. Well, there's also going to be a change in momentum that's attributed to a change in mass. And why this is interesting, or one reason why this is interesting, is because this term is what's responsible for basically rocket propulsion. So back when rockets were first being developed, and this idea of traveling in space was new, there was controversy as to if this would be possible because you're not pushing against anything, right? So we have talked about forces where, if you have a block and one block pushes on another, you're going to get equal opposite forces. Well, if you're in outer space and the rocket is shooting, it's shooting stuff out the back of it, there's nothing for it to push against. It's pushing into a vacuum. So how would you have a force to push the rocket forward? This was kind of the idea and the source of this confusion. Well, it turns out if you look at Newton's second law, if you look at the change in momentum with respect to time and include the fact that the mass could change, then it naturally addresses this question. So there's a whole section in this chapter about rocket propulsion. Hopefully we'll get a chance to talk about that in a little more detail. It's definitely an interesting topic, and it connects with stuff we've talked about with gravity, and it connects with just this larger picture of how calculus is really the way to go when describing physics, when describing phenomena in physics. So wanted to mention that. which is kind of a cool topic. So, and then the next thing is, now that we know what momentum is, we've made this connection to Newton's second law, let's talk about momentum conservation. So this is section 9.2. Conservation laws, so we're familiar with this in that we just talked about energy conservation. Let me write out the definition, and then I'll give you sort of a cartoon. Try and write as neatly as possible. So when no net external force acts on a system, the total momentum of the system is conserved. So the sort of cartoon picture of this is like what was suggested in the chat. You imagine objects, so sort of the prototypical example to visualize is to think of things like pool balls. And the way that it's described in your book in terms of subscripts is using letters to represent different objects. So kind of the prototypical example is you have some pool balls or something that hit each other, they collide. That's not a very good, let me see if I can. They collide, and you can imagine after the fact, it's going to move off at some different velocity, so we can use a prime, sort of like an apostrophe, to represent that velocity after the collision. And this is kind of the sort of prototypical cartoon way that we present. Let me make this a little bit bigger. Separate these. So a couple objects, they hit into each other, and then they move off in different directions. And the main idea is just that the amount of momentum, so mass times velocity before, is going to have to equal the mass times velocity after for all the constituents. And we can write this mathematically as and so I suspect if you've messed with this before, this is kind of the picture that you have in your mind. A couple objects whack into each other, and they maybe move off in different directions. And we can state this another way that's kind of a nice alternative that's presented in your book, which is, it's a nice concise way of stating it. The total momentum in an isolated system remains constant. And the reason that I like this is that they use the word isolated. So this gets at the notion that this picture is not is a circumstance where there's not some external force that's working on it. So think of this as being one way to think about this is as being sort of a box where there's no external forces. Um, and we haven't really worked with much for non-conservative, or sorry, non-contact forces except gravity. So you can imagine, suppose there's a circumstance where you don't have gravity, the amount of momentum when you add it up is going to have to remain the same. You can't have an object that's just speeding up, that's acquiring momentum, unless there's some external force that's acting on it. So gravity being the one that kind of comes to mind. So if there was gravity, you could imagine these objects falling. They're speeding up. Their momentum is increasing. Um, so I think it's a good conceptualization to think of it as being isolated, like in a box or something, where there are no forces that are acting on it. Um, so this is the idea of momentum conservation. In terms of what you're going to end up doing with this in this chapter, I'll put a note here. That's basically figuring out how to conserve momentum in 2D, 3D is the meat of this chapter. So that is the main obstacle, the main challenge with this chapter. It's easy enough to state this. You know, it's just the momentum that you start with has to equal the momentum that you end with. Okay. Where it becomes more difficult is to consider if you're in more than one dimension, you have uh, velocity components in x and y and possibly z for multiple objects, and you have their velocities. So you can think of it as magnitudes and angles, or separate components for x and y, and you have to keep track of all of those. So the main result of this is that you can end up with a fair amount of algebra because you have a lot of components for each object and each object before and after. So I'll just put a note. And this gets at the comment about elastic and inelastic collisions, because depending on the kind of collision, you have different relationships that you can make. If it's an elastic collision, then you'll be able to conserve energy, and you can use that additional piece of information. If it's inelastic, you can't. But we will talk about the different kinds of collisions and go into more detail on that. Not today, but next time. But this is kind of the concept. We'll look at some simple examples of this in one dimension today to kind of get you started, and then we'll get into this more complicated issue of what happens in 2D and 3D next time. So does that all sound fairly familiar so far? Any questions? So I would encourage you to look at section 9.2. The stuff that I've described to you is basically right out of section 9.2. I'll try and use the same sort of notation that they use so things are consistent. But how are you doing with that? Questions? Doing all right? Um, is it the derivative? Oh, so it's not a derivative of velocity. It's just the velocity after. Yeah, so a clarification in terms of notation. So it occurs to me that question maybe speaks to, so like if we have VA, this would be initial velocity. Ah, sorry. VA would be initial velocity. VA prime would be the velocity after a collision. Very similar looking VA dot. We saw this notation in lab. This could be, yeah. This could be a derivative with respect to time. So just a clarification in terms of notation. Yeah, you could use whatever you want. If you would rather use VA naught and VA, that's totally fine, or VA final or whatever. I've told you this before. I think you should use whatever notation you find works best for you. Of course, it's important to just be consistent, to stick with what you're doing. This becomes evident when you work with these problems in more than, in 2 or 3 dimensions, because you end up with a lot of components. So if you are not careful with your subscripts, if you're not careful about kind of keeping track of everything, it's easy to make algebraic errors. So use whatever system works for you. I'm showing you with the primes because that's the way that they describe it in the text at that point. So, but yeah, when you're working problems and stuff, you should do whatever works best for you. So let me show you one other idea. I suspect it seems people are fairly comfortable with this idea of momentum conservation, and then we'll work some problems to kind of get your skills up with that. So the other thing that I wanted to mention is in the next section, and this is a nice calculus connection. And this gets at the idea of something called impulse. So, and this is a useful concept when we're discussing collisions and impacts. So recall, we've just talked about how we can state Newton's second law like this, if I can write legibly, that force equals dp dt. Well, we could reorganize this. That force times a differential, time differential, is going to equal a momentum differential. And we could then, the natural thing to do with this would be to integrate it. So if we integrate differential momentum, you're going to get a change in momentum, because that would be P evaluated from initial to final. So this would be change in momentum so final momentum minus initial momentum is equal to this quantity, the integral of force. Now, this is impulse. Now, your book, for whatever reason, uses the letter capital J to represent impulse. I don't find that to be particularly illuminating, so I'll usually just call it impulse. And in practice, it's difficult. So consider if you have like a we'll look at a problem on this today, but if you have a collision, a lot of times the force as a function of time is not something that you have a function that you can describe cleanly with a function. So you can imagine, you hit something with something else. There's got to be like some big spike in force. But describing what that is mathematically can be challenging. So part of what's useful about this is that we can use this idea and say if you have some interval over which you knew that it was the force was applied, you can come up with an average. So in other words, you can represent this as an average force times some time interval. So if, for example, if you hit a baseball with a bat or something, if you have a sense of the duration of the impact, you can use that to get an estimate for the average force, where the area of these two things is the same. So actually, let me try and sketch this a little more cleanly. So imagine this, the curve is the black, and then let me put this in a different color. And then the average force, over this delta t is this rectangle where the blue is average. So, and this is kind of interesting because we can use this, like I said, if we have a sense of the duration of a collision, you can put a kind of an estimate on the average force during that time. So it's not going to be exactly the same because, like I said, it's difficult to analytically to have a function that analytically describes what the force is. In other words, it's difficult to do the actual integration, but in practice, if you know the time interval, you can say something about the average force during that time. Okay, so, and we'll look at this in an example problem shortly, but this is just another definition. This is in section 9.3, so you can look at section 9.3 to see some more description of this. But is this an idea that you've encountered before? Have you encountered impulse? Ah, excellent. Oh, okay. So some have. What about other folks? Have you encountered impulse? Let me know in the chat. Oh, wow. Okay, so people are a lot of people have seen this. All right. Yeah, it's totally fine if you haven't seen it. We're not going to be doing, uh, we're not going to be trying to evaluate the actual integral. It's just the idea to know is pretty important. So yeah, no, don't sweat it. We're not going to be looking at some hairy integrals to try and come up with, the change in momentum based on the integral. Mostly we just use the average version. So, okay, let me show you a few example problems to get you started with this material. So the first question. So these are some simple questions, basically looking at momentum conservation in one dimension. So here's a question for you. A 9,000 kilogram railroad car travels along on a level frictionless track with some speed, 15 meters per second. A 4,350 kilogram load initially at rest is dropped onto the car. What will be the car's new speed? So this is an example of momentum conservation in one dimension. Let's try and give ourselves a cartoon of what's going on here. So we have some railroad car. It's going to have some load that's dropped into it. Initially, the car is traveling at 15 meters per second, and it has a mass of 9150. So what's going to happen is we're going to add that mass, and we want to know what's the velocity going to be afterward. Let me call that VA plus B. And so what do we do? Oops. So it's a application of conservation of momentum. Oops, not forces, momentum. So the initial momentum is going to have to equal the final momentum. What's the initial momentum? Let's call the train itself MA. The load that we're going to add is MB. So the initial momentum is just MA VA. This is going to have to be equal to the combination of masses, MA plus MB, times the velocity A plus B that we're solving for. We can then solve this for VA plus B. Put in our numbers here. Crunch the numbers. We find that this would be 10 meters per second. So the speed after adding the mass is going to be less in this situation, which I think agrees with our intuition. You add a bunch of mass to your train car. That mass is at rest. In order to conserve momentum, if the mass goes up, the velocity is going to have to go down. So this is an example of basically the simplest type of momentum conservation question you can have. You have your momentum is in one dimension, and you're just changing changing the mass. Okay, so that's a simple example. Questions on that guy? Pretty straightforward. So let me show you a very similar question. Another one-dimensional question. Let's take a look at this one. So we have an atomic nucleus at rest decays radioactively into an alpha particle and a smaller nucleus. What will be the speed of this recoiling nucleus if the speed of the alpha particle is 2.8 times 10 to the 5 meters per second? Assume the recoiling nucleus has a mass 57 times greater than that of the alpha particle. So this is also a one-dimensional momentum conservation question. So something that jumps out when looking at this question is the nucleus is at rest. So in terms of talking about momentum, what that means is that the initial momentum is going to have to be 0. because there's no initial velocity. Um, so let's just try and draw a little cartoon of what's going on here. We have some kind of a atomic nucleus, and that thing is going to decay. It's going to break up into a chunk that's most of it, and then also an alpha particle. Do you guys know what an alpha particle is? Have you heard of an alpha particle? Yeah, it's helium. It's basically a helium nucleus. So um, yeah, so it's interesting. There's different kinds of radiation. Alpha particles are there's alpha, beta, gamma radiation. Gamma radiation is basically electromagnetic wave radiation, uh, like X-rays and stuff like that. Um, Beta radiation is basically electrons or things that are similar to that, and alpha radiation is like a helium nucleus. So, and this can be nasty. It can't really, if you like eat stuff that's been contaminated with alpha particles, it can be really bad. So, in any case, what's relevant for us for this is that just for our kind of picture of this, so it would have the couple protons and neutrons and give us a helium nucleus. And then the other thing that's relevant here is that ionizing radiation. I'm not actually sure what ionizing radiation is. I'd have to see the context. But generally, so ionizing radiation, if I'm remembering correctly, if you have something that causes other things to be ions, i.e., something that's energetic enough that it's kicking out electrons, that is doing some damage. So, um, yeah, but that's an interesting. I think in 2021 or 2031, you talk more about radiation. 2031 probably. But that's a whole fascinating subject. I wish we had time to talk more about it here, but alas. Um, but there are some actual really interesting connections between particle physics and momentum conservation because, you know, particles are actually some of the only things that obey elastic collisions, um, as opposed to macroscopic objects like pool balls and stuff like that. You may see in problems that they tell you they collide elastically, but not really because you have energy that's going into deforming the pool balls. With particles, you can have actually elastic interactions, which is interesting. But in any case, so this simple problem, if we know the mass and the velocity of the alpha particle, and we know the mass of the remainder, we can find uh, we can find the velocity. So how do we do that? Well, let's look at conservation of momentum. The initial momentum is going to have to equal the final momentum. The initial momentum is actually 0 because the thing is at rest. So that's going to equal the mass of our alpha particle times the velocity of the alpha particle plus the mass of our 57 alphas times the velocity of that. Actually, let me write it like this. And so notice the mass, since they give it to us as a multiple of the alpha mass. This is common and it would cancel. And then we just have, we would subtract and solve for the V57. Notice this would become negative V alpha divided by 57. So if this is 2.8 times 10 to the 5, divide by 57, this becomes, careful, negative 4.9 times 10 to the third meters per second. So this seems very simple, but there is sort of a, it's not surprising per se, but it is pretty deep idea here that this negative sign is telling us that if the alpha particle is going one direction, the rest of it has to go in the other direction in order to conserve momentum. So this negative sign is very important. Even though this is only a one-dimensional problem, the negative sign tells you it's going in the opposite direction. Which you need in order for it to conserve momentum. And now if you only have two particles, you can only have them go in opposite directions. In other words, you cannot have this situation. You can't have like one particle go like have it break up. You can't have one particle go like that and one particle go like this, because the net momentum then is in this direction. So that would not be allowed. And we'll talk, we can talk more about some of the particle physics connections with this. But that's just, it's interesting, I think, that a really basic idea can kind of set some constraints. It kind of sets some limits on things. And this is all just based on one-dimensional momentum conservation. All right, so let me show you one other example. Just because, and I'll try and, we only have a couple minutes, but I want you to be exposed to this idea of impulse. So here's an example. A golf ball of mass 0.045 kilograms is hit off of a tee at a speed of 45 meters per second. The golf club is in contact with the ball for 3.5 milliseconds. Find the impulse imparted to the golf ball and find the average force exerted on the golf ball. So we only have a couple minutes, but I think we can kind of get the drift of this. We have a golf ball. It's, I can't draw a golf club at all, but it's hit by a golf club, and then it's going to have some velocity, 45 meters per second. Now, our definition of impulse is just the change in momentum. So it's the final momentum minus the initial momentum. The initial momentum is 0. The thing is sitting on the tee. So and the final momentum will be just mBVB minus the initial momentum of 0. So this would be 0.045 kilograms times 45 meters per second. So 2 kilograms meters per second is the impulse, the change in momentum. And then the other thing that they want is the average force. So I had talked to you about how, and that would correspond to this. If we know the approximate duration of the impact, we can spec the average force. So the average force times that change in time, that time interval, is the same thing as the impulse. So in other words, if we want to spec the average force, we divide by that delta time. So 2 kilograms over 3.5 times 10 to the minus 3, and we get 580 newtons is the average force. And something I would point out, just conceptually, is that notice the average force is this, it's square compared to the shape of the actual interaction. So if we were to spec like the peak or the max force has got to be larger than the average force. So this using the impulse to specify the average force is, useful. It gives us a feel for that interaction, but it's actually going to be less than the peak, presumably. So it's just kind of interesting, I think, or just a quirk, or just a notable piece of information regarding the connection between average force and actual force. If we had like access to the force as a function of time as an actual function, the the peak of that is going to have to be a little bit larger. Could be really, much larger depending on how we have it set up. In any case, just something to notice about this. So that's impulse. So there's an impulse question, I'm pretty sure, in your homework. We did a couple simple questions with one-dimensional momentum conservation. So next time, we'll get into momentum conservation in more than one dimension. So be sure to read, chapter 9. Questions? So I'm trying to be better about ending when to give you passing time and everything. So I want to wrap up here. Questions? I think it sounded like many folks were familiar with impulse, and this idea of momentum conservation is relatively familiar. So I think you'll find this stuff not too bad. Yeah, pretty simple so far. And then when we get into 2D, it's going to be more, the algebra will be a little bit more involved, but the concepts are not super complicated. You have the momentum before and the momentum after, and they have to stay the same. So it becomes the math becomes the main issue. So, and it's not conceptually difficult math, it's just algebra. Other questions? If there aren't any questions, have an excellent day. We will see you tomorrow if you have lab tomorrow, or we'll see you on Wednesday like I said, when we get into conserving momentum in more than one direction. So yeah, okay, well. If you have any concerns too that you don't want to voice here, contact me on Teams, contact me via email. We can work on homework problems, work on outstanding labs, anything that you may have questions on. So, okay, well, have an excellent day, and we will see you soon.